All right, welcome back. I know it's been a little while since I've posted a new lecture video, but am trying to get caught up here. And today, or in this video, I should say, I'll talk about cell potential and concentration, and I'll also introduce the Nernst equation. So far, we've just looked at cell potentials when all of the solution concentrations are 1 molar. And that's part of the definition of standard reduction potential. We have standard conditions. So gases are 1 atmosphere, solutions are 1 molar. But we can ask the question, what if our concentrations don't equal 1 molar? What if they don't equal 1 molar? Well, we should use Le Chatelier's principle. So let's just take a look at an example here. So let's say we had 2 aluminum solid plus 3 Mg2 plus, this, and that's going to go to 2 Al3 plus aqueous plus 3 Mg solid. And in this case, our cell potential is, what do I have here, 0.48 volts. So E naught cell equals 0.48 volts. All right. Now, if we increase, let's think about this for a minute. If we increase the amount of products, okay, so if we increase, let's say, our magnesium, then it's going to drive the reaction towards the reactants, and that will result in a, sorry, I just did that backwards, didn't I? If we increase the amount of reactants, that will drive the reaction towards products. And we can think of our potential as being a product of sorts, just like if we had an exothermic reaction, we would think of heat as being a product. So adding, let's say, magnesium shifts the equilibrium towards the products and would increase the potential. So we will say here, increasing reactants, and of course these brackets mean the concentration of reactants. Increasing reactants increases our cell potential. So E naught cell. And if I say, I won't say decrease, I would say increase the products, increasing our concentration of products will drive the reaction back towards the reactants and result in a lower cell potential. So this is something we will have to take into consideration. And the best way, I think, to do that is to just jump into what's called the Nernst equation. So here, let me pause so you guys can pause. Okay. So let's look at the Nernst equation. Okay. So if we go back and look at chapter 17, we can see that delta G equals delta G naught plus RT ln of Q, where of course Q is the reaction quotient. Okay, just like way back when we were first doing equilibrium, chapter 13, we had K, so K goes into delta G naught. Q is the reaction quotient, what concentrations you actually have, and then you can figure out. Remember, we used Q to figure out, oh, is the reaction going to go towards products or towards reactants? Now, from last time we saw that delta G equals minus N F E naught. So we could go ahead and plug these in. I should say, sorry, delta G equals minus NFE. So we can plug things in and we would get minus NFE equals minus NFE naught plus RT ln of Q. Okay. Or we could go ahead and combine our NF factors on one side, and what we get is ultimately we get E equals E naught minus, sorry, I'm about to write a delta, but it's not a delta, it's just an R, minus RT over NF times the natural log of Q. Now, one important thing to remember is that, R is the gas constant, but we want to use the value of 8.314 joules per mole Kelvin for our value of our gas constant, okay? Using the value that has units of liter atmospheres per mole Kelvin is not going to work. I guess apparently a joule actually is the same energy as also liter atmospheres, which is kind of weird, but maybe you can think about that for a minute. Okay, but this is our Nernst equation right here. So if we have a system that is not at 1 molar for all the concentrations, then we would use the Nernst equation. We take the E naught, which we would typically get from a table, and then we plug in our actual concentrations. We need to figure out how many electrons were transferred. And so on Monday's workshop, I'll go ahead and go over some problems like this. F, of course, is the Faraday, R is our gas constant, T is our Kelvin temperature. Now, normally, under standard conditions, we're at 25 degrees Celsius. So this will simplify to the following. E equals E naught minus, now at 25 degrees Celsius, we know that's 298 Kelvin. R is a constant, F is a constant. We can actually convert from the natural log of something to the log of something. So we can say that ln of x equals 2.303 log of x. That's a little aside there. So, delta G equals minus RT ln of K, delta G equals minus 2.303 log of K. So we can actually substitute in 2.303 log, where that's the base 10 log. I don't know, engineers like base 10 more? I don't know, maybe. I should ask my engineering friends about that. That's a good question. Anyway, so we can plug in these numbers, and what we end up getting with is 0.0591 over n times the log of Q. So this is an alternative expression for the Nernst equation, but it's only at 25 degrees Celsius. So notice we switched to log from natural log. So if you're not at 25 degrees Celsius, you have to use this. If you are at 25 degrees, you can use this one. You don't have to plug in as many numbers here. There are units here. I forget what the units are. They're units of volts is what the units end up equaling. So there's a unit associated with that constant, but don't worry about it. All right, so that's the Nernst equation, and this would allow us to determine a cell potential when the concentrations of our solutions, reactants, and products are not equal to 1. And again, in the next workshop, I'll go over some of these. Now, let's take a look and see if we can say something smart about this. So let me erase here, and then I'll rewrite the Nernst equation. So erase. And let me just copy it down here. So E equals E naught minus RT over NF ln of Q. So there's a couple of interesting things that we can do here. One is we can make what's called a concentration cell. So let me just set that guy aside. I have a concentration cell. And in a concentration cell, we have the same product and reactant. We have the same thing doing oxidizing and reducing. So products and reactants are the same. The only difference is their concentrations in the half cells different. So we have, so this is a voltaic cell with same half reactions for oxidation and reduction. Concentration is only difference. And so there's an example in the text of a silver concentration cell, and that's actually an example that you deal with in the lab, which hopefully I'll have posted soon. So let's take a look here. So let's say, for example, we had, so e.g. a silver concentration cell with 1 molar Ag plus on one side, 0.1 molar Ag plus on other side. Okay, so we'll just make, actually, let's make that 0.01 molar. 0.01 molar. Okay, and could probably, well, we'll leave it at that with sig figs for now. I'm not going to worry about it here. So we could go ahead and plug in our values here. Okay, so first of all, what would this look like? Well, what we would have is the following. We'd have our, so here's our porous disc here, and then we'll have a plate here of silver, and then a plate here of silver, and then Ag plus, we have a wire connecting, and we've got 1.0 molar here, 0.010 molar there. I'll give these guys an extra sig fig. There we go. Okay, now let's think about it for a minute before we plug in numbers into the equation. Now, if these were both 1 molar, there would be no current flowing because they're the same on both sides, so nothing happens. But if we have 1 molar silver over here, let me add in my electrolyte here, there we go. We have 1 molar silver plus over here on the right, and 0.01 molar on the left. Well, by Le Chatelier's principle, this side should try to get lower in concentration, and this side would try to get higher in concentration. So what that means is that silver ions here will actually start sticking to the silver strip, but they need electrons to go from silver plus to just solid silver. And those come from over here. So our electrons are flowing that way. And as the electrons leave the silver strip here on the left, we get more silver plus ions. And as they go to the silver strip on the right, the silver plus ions pick those up and become solid silver. And that's going to increase the concentration of silver plus on the left, decrease the concentration on the right until we get to some kind of equilibrium. And of course, we've got the porous disk there to, for the counter ions and stuff. But conceptually, this is what's going on. So we should get a slight electron flow from the less concentrated to the more concentrated. So we should have a positive potential. Let's see if that happens. So E is going to equal 0.0 volts. How do I know my E naught is 0 volts? Well, at standard conditions, we have no potential. Remember, if both of these concentrations are 1 molar, there's no potential. So we've got 0 volts minus, and I'm actually going to plug in the other equation. Let me write it up here real quick. Or E equals E naught minus 0.0591 over N log of Q. Okay, so let's use that one. I'm going to assume that we're at 25 degrees Celsius. If I don't tell you what temperature we're at, assume it's standard, and you can always ask. So you can always email me, etc. For the take-home quizzes and stuff. All right, so let's plug that in. 0.0591. Now what's N? Well, if we're going from Ag plus to Ag, we're just transferring 1 electron. So for a concentration cell, so for other Nernst equation problems where you don't have the same reaction, you really need to write it out and figure out what N is. Or if you had a concentration cell that, let's say, was copper on both sides. Since we're going from copper to copper 2 plus and copper 2 plus to copper, we've got 2 electrons transferred. So you do need to figure out how many electrons are transferred. So that's just divided by 1. And then we've got the natural log, the log base 10 of Q. Now we've already figured that we're going from here, the electrons are flowing from here to there. So we should have, let's see, the electrons are going from there to there. I'm just trying to remember which way we want to put in our numbers. So we will have, the product should be 0.010 molar and 1.0 molar. I believe that is correct because we are increasing silver concentration over here and decreasing it over there. So, so this would be our product, because we're getting more Ag plus on that side. So we treat it that way. If you actually had a reaction that wasn't a concentration cell, so if you're actually applying this to other situations, it would be easier to figure out reactant and product. But drawing a diagram like this and trying to figure out which way the electrons flow is helpful for doing a concentration cell. Well, 0.01 divided by 1 is just 0.01. Log of 0.01 is -2. So our cell potential is going to be 0.0591 times 2. Oops, I have to use the right finger to open up my phone to use the calculator. And calculator 0.0591 negative times 2 negative equals 0.12 volts. Okay, I believe that is correct. Hopefully I get my math right. Oh, that'd be point, so yeah. So to 2 sig figs, it's going to be 0.12 volts. That's not a lot. Concentration cells will not have a very large potential. Okay, so we've seen the Nernst equation, and we've seen how it applies, or it can apply to concentration cells. Let's do one other thing. Pause for a sec, you guys can jot this down. Okay, one last thing I just want to show you. And it'll be a transition to the next topic, so the next video. So this potential is before any flow has occurred. So we could ask the question, what if Q equals K? So what if we are at equilibrium? So, i.e., what if we're at equilibrium? Well, if Q equals K, then what do we have? We've got E equals E naught minus RT over NF, ln of K, but this right here is just delta G over NF, which is just E naught. So that would equal 0 volts, 0.0 volts. And this is what we call a dead battery. Okay, when our Q actually equals K, then we end up with a dead battery. All right. Okay, so we'll take a look more at batteries in the next lecture. And until then, I will see you guys later.